So compared to the UDP header, what do you notice? Lot more fields, right? So the source port and the destination port are essential for multiplexing, demultiplexing. So TCP also supports them. As part of the sliding window protocol, you need sequence number and acknowledgement fields. So these fields account for that. Earlier, when we talked about sliding window protocols, we said a packet has sequence number 0, this next packet has sequence number 1, so on and so forth. But things are handled differently by TCP because it's a byte-oriented protocol. So let me get into the details. In TCP, each byte in fact has a sequence number. And if you have a segment that is carrying some data as part of it, the sequence number field that is as part of the header is going to contain the sequence number of the first byte as part of the data. And similarly, the acknowledgement field that you are going to carry as part of the segment is going to acknowledge data of the flow from the other direction. And another twist with respect to TCP is that this acknowledgement field is going to carry the sequence number of the next byte this particular host is expecting. I think an example will make things clear, but before I get there, unless otherwise specified, the TCP ACK is considered to be cumulative. So let's look at this example. In this example, both A and B want to exchange data with each other. And in the past, maybe a few other segments were exchanged. Currently, we are focusing on this particular segment. This segment has a sequence number 20 and the data, that is the payload of this segment, is 1000 bytes. So what this means is out of this 1000 bytes, the first byte sequence number is 20. And this segment is acknowledging some data that was in the past sent by B. And the fact that it is saying 857 means that A is asking B to send data starting at byte 857. So in response to this segment, B is now going to send a segment. So this is the segment that it sends. Since it is asking for 857, so this segment starts at 857. And this segment, the payload in this is 100 bytes. And see this acknowledgement. It is acknowledging this segment, whereby because this byte starts at 20, this is of 1000 bytes long, it is now asking for this byte, which is 1020. So that is how the acknowledgements work. So in response to this segment, A is now going to send another segment. So you tell me what is the sequence number of that particular segment? And what is the ACK field of that particular segment? Well, the sequence number will be 1020 because this is what B is asking. And you are acknowledging this particular segment where again this is 100 bytes, this first byte is 857 and you want this byte which turns out to be 957. So that's with sequence number and acknowledgement. Following this is the header length. So you specify what is the header length. You need to specify this because there are options here. In case there are no options, the TCP header length is 20 bytes. Then there is this reserved field which is set equal to 0. Following this are the flags. So let's look at flags UA, PR, SF. So U here stands for the urgent flag. So whenever this flag is set in a segment, it is indicating to the receiver that there is some urgent data as part of the segment and thereby pass this data to the application right away. And this urgent field is associated with an urgent pointer. So that's here. And this urgent pointer specifies where in the segment non-urgent data begins. So there is an assumption here that the urgent data begins right after the header. And this specifies in bytes what is the length of the urgent data. This A flag is the acknowledgement flag. So whenever a segment carries a valid acknowledgement, this bit is set equal to 1. Thereby, the other end can interpret the acknowledgement field appropriately. So sometimes the data flow is only in one direction. Thereby, you don't have to interpret the acknowledgement corresponding to the other direction because there is no data flow in the other direction. P stands for push flag. At times, you want to indicate to the receiver that whatever data is in the buffer, push it to the application process. So this flag is not used. Similarly, the urgent flag is also not used. R stands for reset. So whenever this flag is set, it is indicating that whichever set this flag wants to abort the connection. Basically, you make use of reset whenever you receive some data which confused your state. For example, some packet with a sequence number that you should normally not see, in which case you are going to reset the connection. Similarly, the SF flags stand for synchronization and finish flags. They are short for syn and fin flags. These are used during the connection establishment and termination. We will see more of this later when we talk about connection management. So following the flags is the advertised window. This is part of flow control. So when I cover flow control, I'm going to get into the details. And just like in UDP, you have a checksum field. So this checksum field is compulsory both in IPv4 as well as IPv6 because TCP offers reliable service. And again, much like in UDP, this checksum is calculated over the TCP header data as well as a pseudo header. For the pseudo header, you take the source, destination and protocol fields of the IP header, and not only that, you include the TCP segment total length. Notice that there is no such field as part of the TCP header. This total length actually has to be calculated. So these option fields are used during the connection setup time to negotiate certain parameters, and they are also used later to carry certain information to implement certain functionality. For example, you could use option fields to negotiate maximum segment size. For example, A may tell B that it wants to use a maximum segment size of 1, and B may tell A that it wants to use a maximum segment size of 2, in which case both of them will use min of these two values as the segment size as part of the connection. These maximum segment size have a relation with the MTU that is supported by the network to which these two hosts are attached. By exchanging this information, you basically choose an appropriate value of MSS and thereby an appropriate value of MTU. Now, does this mean fragmentation will never arise at the IP layer? What do you think? Well, no, fragmentation can still arise because this negotiation is being done end to end at the process level. Routers are not involved as part of this. This is just an optimization. Options fields can also be used to perform what is called window scaling. So this is part of flow control. So if you see the advertised window field, this is 16 bits, which means the receiver can tell this buffer size, and because you are using only 16 bits, the maximum buffer size that can be accommodated is 2 to the power of 16 bytes. But what if you want to allocate more buffer because you want to operate with a window size that is greater than this? In which case you will use this option fields to indicate, say, a value of 3, whereby you are saying whatever is specified in the advertised window field, you multiply it with 3 to use as the window size. I think this point will become clear only after I cover flow control. We talked about selective acknowledgements before. These are much more efficient than cumulative acknowledgements. Now, if you want to use these features, you can do so using the options field, where at the connection setup, you can indicate that I can support selective acknowledgements, and if both sides agree, henceforth they can use selective acknowledgements, and the actual selective acknowledgement data information is also carried as part of the options fields during the data transfer. Similarly, the checksum that is employed as part of TCP is not a very sophisticated algorithm. It is a function of the 16-bit ones complement algorithm that I mentioned earlier. But if you want to use a more powerful checksum, options fields let you use a more powerful checksum. There are more options than this, but I think you get the idea as to how options fields are used. So to summarize, TCP is a very popular, finely tuned protocol. It provides quite a few features: reliable data transfer, full duplex operation, flow control, congestion control, so on and so forth. At the heart of TCP is the sliding window protocol. We also examined the TCP header. Up ahead, we will see how the TCP establishes connections as well as tears them down under connection management.